Recording, am I getting audio? I seem to be getting audio. Not much audio, but we'll see. Okay. Since we are falling behind quickly, we're going to go ahead and start early so we can work on a couple of these homework problems, get y'all going. But y'all really do need to make a point of getting the homework done and turned in on time. Because I can't go through the semester like this, at halftime, or I'll be completely buried under work by the time we get to the end of the semester. So, I'm going to look at 15 and 16 very quickly. And then we're going to start covering the new material of electric fields and vectors. So, where'd the book go? Here it is. Problem 15. 4 charges at 4 corners of a square of L on each side. We got Q, L, 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 and L. And we got 2Q, 3Q, and 4Q going clockwise. Q, 2Q, 4Q, 3Q, and 4Q, and they want to know the magnitude and direction of the force on the charge 2Q. All right. That means there are 3 other charges. Each one of them is exerting a force on 2Q. 2Q is also exerting the same force on each one of them. So if we're looking at the force from 3Q, it's going to be pushing on Q. It's going to be pushing in that direction. The force from 3Q. The force from Q is going to be pushing in that direction. The force from 4Q is going to be pushing in that direction. So we've got to calculate 3 vectors here and then add them together to get the net sum total force acting on Q. On 2Q. So first, let's start with force from Q. And it is equal to K times Q times 2Q divided by L squared. Right? What's 9 times 10 to the 9 times 2 is what?
18.
Yes. You know what? Let's not worry about that just yet. We're just going to write this.
How'd you get 2? Where'd you get?
Because this charge is 2 times Q.
Oh, okay. All right.
This charge is 3 times Q, and this charge is 4 times Q.
Okay.
That's a scalar multiple. That is not a subscript.
That clears things up for me.
Yep.
I thought it was just a label.
So we're just gonna write, I'm just gonna keep that as K times 2 times Q over L squared. Now, we know there's really not a whole lot more to simplify there. What's the direction? Well, the direction of this force is at angle 0 degrees, straight that way. Now let's look at force 3Q. Again, it's K, and now it's 3Q times 2Q divided by L squared, which is equal to K. 3 times 2 is 6. Q squared over L squared, or K 6 Q over L squared. This time at an angle of, I'm doing 3Q. Be at 90 degrees. Now let's talk about the force from 4Q. It's K times 4Q times 2Q divided by, what is this distance? This squared is equal to this squared plus that squared. The square root would be the distance.
Yeah,
we
we're
want the distance squared in the denominator. So yeah, D equals the square root of L squared plus L squared.
But then the square from over here, we just cancel out.
D squared would equal this. All right, so that we write as K times 8 times Q squared divided by 2 times L squared. See the 2? 8 over 2 equals 4 Q over L squared. But now, at what angle?
11:45, since it's in the middle of 90 and 0.
It would be. Well, it's the tangent of L divided by L. What's the tangent of 1? Or the inverse tangent of 1? Let's make sure. Plug it into our calculator. Right, 45 degrees. Now, all we got to do is add these 3 vectors together. But how do we do that? First thing you got to do, if you want to add vectors, convert them into Cartesian coordinates. Our first one is at 0 degrees. And it is K times 2, it's 2 times K times Q over L squared. At an angle of 0 degrees. So it's going to be that magnitude times the cosine of 0 degrees times I, plus that magnitude times the sine of 0 degrees times j. Remember the unit vectors I and j? Does everyone understand how I'm converting this from polar into rectangular coordinates?
I can't remember exactly I and J. I remember you writing that down.
I is the horizontal unit vector,
Okay.
J is the vertical unit vector.
Gotcha.
So the components of this vector are the magnitude of the vector times the cosine of the angle. If it's at some arbitrary angle theta, it has this magnitude, then its x component is m cosine theta. That's that magnitude times I, scaling the unit
Since
vector.
I is the horizontal unit, right?
Right? And vertically, it would be this magnitude times the sine of the angle
And that's J.
times the unit vector j. Exactly. So that's the two components of this thing in rectangular coordinates. Real quick, what's the cosine of 0 degrees?
90.
1.
1.
Cosine, plug in the 0, put in 0 to your calculator, take the inverse cosine. Or take the cosine of 0 degrees, not inverse cosine.
1.
So, cosine of 0 is 1. What's the sine of 0?
0. So that would cancel that out.
That means it has 0 vertical component, and the entire thing is horizontal. So, the first one, FQ, boy, that's a dangerous subscript, isn't
Yeah.
it? Okay, we're going to be real careful with that one. Is equal to K2 Q over L squared I plus 0 J. And you can see that if you just look. You know, you can see it's all horizontal. It's all along the x-axis. We're going to find the same thing here with 3Q. Force due to 3Q is going to be, what's its magnitude? K times 6 times Q over L squared. Times the sine. I'm sorry. We're first doing the horizontal, so it'll be times the cosine of 90 degrees, because it's straight up at 90 degrees. That'll be times I plus K6 Q over L squared times the sine of 90 degrees times J.
Cosine 90 would be 0. There should be no vertical.
Cosine of 90 degrees is in fact 0. Plug it into your calculator and confirm it. And the sine of 90 degrees, which you also want you to plug in and confirm, is equal to 1. So, this one becomes 0 I plus K6 Q over L squared times 1 times J. All right? And we can add these two together right now. F of 1 and 3 together will be K2 Q over L squared I plus K6 Q over L squared times J. That's that's the combined sum of 3Q and 1Q pushing on 2Q. And you will notice that they're not equal. So if we then converted this back into polar coordinates right now, we would find it is not pushing at exactly 45 degrees. In fact, since this one is stronger pushing straight up than this one pushing sideways, it would be greater than 45 degrees. It would be somewhere between 45 and 90 degrees that the net sum of those two vectors would be working. But we're not there yet. We've still got this last one. It is at 45 degrees. So, I'm going to come work over here with this one. We've got the force due to 4Q is equal to K times 4 times Q over L squared times the cosine of 45 degrees I plus K 4 Q over L squared times the sine of 45 degrees J. And now, they're not going to, neither one of them is going to cancel out to 1 or 0. What's the sine of 45 degrees? It's the square root of 2 over 2, or 1 over the square root of 2. So is the cosine of 45 degrees. This and this are both equal to 1 over the square root of 2, or the square root of 2 over 2. Either one. Either way, it works out to about 0.707. The square root of 2 is 1.4 something. Now, this one, we write K times 4 times the square root of 2 over 2 times Q over L quantity squared. I plus K times 4 times the square root of 2 over 2 times Q over L squared J. And we can cancel out these 2's. And we end up with K times 2 times the square root of 2 Q over L squared plus K 2 square root of 2 Q over L squared J. I left out the I there. Sorry. Now this is F4Q, which we can add to this. Add these vectors together. Again, all you do is sum the x components and sum the y components. And we end up with K.
K4.
No. Let's write this out carefully. We've got K2 Q over L squared plus K2 times the square root of 2 over L squared. All right? So, let's factor out the K and the 2 and the Q over L squared from both terms. We've got a K2Q over L squared in both terms. So that goes to K2Q over L quantity squared times 1 plus the square root of 2. That's these terms. So that is times I. That's for K2 and K2. But here for J, we've got K6 Q over L quantity squared plus K2 square root of 2 Q over L quantity squared. All of this times J. Well, we can factor out a K. We can factor out a 2. And if we factor a 2 out of here, we end up with a 3 left. So we've got a 2 and a Q over L quantity squared times what's left. We've got 3 plus the square root of 2 times J. Right? So our net total force on Q2 is equal to K2Q over L square root K times 2 times Q over L squared times 1 plus the square root of 2 I plus K2Q over L squared times 3 plus the square root of 2 times J. We can simplify this more because we've got K2Q over L squared in both terms. We can just factor that out. And then that leaves us with 1 plus the square root of 2 I plus 3 plus the square root of 2 J. These are all numbers, so we can punch these into our calculator. K times 2 is also a number. And K is just 9 times 10 to the 9. So let's look and see what form are they expecting this to be in. Okay, now they leave K Q over L squared. So they leave it. They didn't factor out this 2, so we're going to put that 2 back in. They leave it with K times Q over L quantity squared times 2 plus 2 times the square root of 2 let's do these, let's punch these numbers into our calculators and see what we get. 2 times the square root of 2 plus 2, that's 4.83. I plus 8.82. J. All times KQ over L squared. That's the vector form of that total net vector. But they want to know the magnitude and direction. So we now need to convert this back into polar coordinates. Right? Clear out some space. I ain't erasing nothing that I can't reproduce quickly. I need to. What's the magnitude of this vector?
When you have to times K times those numbers down there, the I and J. Or no, the I and J is your direction.
K is just, we're leaving K as a constant out front.
Okay.
So K times Q over L. That's just the scalar constant. What we need to do is find the magnitude of this part here. So we've got that times 4.828 I plus 8.828 J. What would the magnitude of that be? We would take, becomes K times Q over L squared times 4.828 squared plus 8.828 squared. Make the square root of it. Pythagorean's theorem. So we've got 4.828 squared plus 8.828 squared equals 101.24 squared, and if we take the square root of that, we get to three significant digits, we get
We can take the square root of.
the square root of the sum of the squares. It's just Pythagorean's theorem.
2.062. We're taking out the 3 significant figures.
So to 3 significant digits.
10.1. Okay.
.1 times KQ over L squared. Now, what's the angle? This is your vertical, this is your horizontal. Theta will equal the arctangent of 8.828 divided by 4.828, which is take the inverse tangent. And that's how that's done. Now, work 16 because y'all desperately need to know how to do 16. The exam you've got coming up on Monday. They're not all going to be easy. That's why I said paper's cheap, trees are a renewable resource.
So the answer from that was 61 degrees. But then also the K times Q squared L squared 10.1.
Yeah, you've still got a K times Q squared over L squared. Technically, if we could have added the 9 times 10 to the 9, we could have treated that K as a number 9 times 10 to the 9, and we'd have still gotten the right, we would have still been correct, but it wouldn't have been 10.1 and 61 degrees. It would have been 10.1 times 9.9, or 9 times 10 to the 9.
That one was tough. I mean,
Well,
yeah, you did it.
now we're going to do number 16. Take notes. This is going to be, you're going to get one like this on your exam. So, fairly warned. Here's our electroscope. And from it are hanging 2 massless strings we don't have to worry about. And they're suspended from them are 2 spheres. They're 21 grams each. And each one of them has 1/2 of Q charge. They are both repelling one another, so they stand out at 26 degrees from the horizontal, from the vertical each. Now, what total charge Q must have been applied to the electroscope? That's what we got to solve for, is Q. So,
If we solve for one, we're going to solve the other because they're the exact same mass, exact same angle.
well, in order for a charge to exert a force, to have a force exerted on it, there must be another charge exerting that force. So the force that Q, this one, exerts on here is the same force that this one exerts on here. Because when you do Coulomb's law, you multiply by both. This Q times that Q, or Q over 2 times Q over 2. In this case. But first, you're going to have to go back to Physics 1 and think about the mass times acceleration equals the sum of the forces. What forces are acting on this ball? You got gravity pushing straight down. which is
9.80.
9.8 meters per second squared times
20 point, isn't it?
there you go, 0.021 kilograms. Yes, 21 grams is 0.021 kilograms. So that's the first force. Force, gravity. Newtons. Kilograms, meters per second squared. I don't know. What other forces are acting here? There's the electric force exerted on this. We'll get there. Let's not confuse ourselves. Let's take this one step at a time. Okay? Because I want you to see how all of this is, how we're analyzing all of this, step by step. There's you were in the military. Were you ever in the military? Any of you else in the military? Have you ever heard the expression, slow is smooth and smooth is fast? Yeah. One step at a time. Take it slow, go smoothly, we'll finish a lot quicker. Okay. The electric force, what is that? Coulomb's law. Okay. Q over 2 times Q over 2 divided by the distance between them squared. What's the distance between them?
We don't know the distance between the two, right?
No, but we know this length.
Yeah, we know that's 78 centimeters.
78 centimeters, or 0.78 meters. And we know the angle is 26 degrees. So what is this distance here?
This is where you use the diagrams.
Well, no, not quite. This time we're going to have to use straight up trigonometry.
Okay.
The hypotenuse times the sine of the angle equals the opposite side. So, 0.78 meters times the sine of 26 degrees equals d over 2, which is say again? No, just d over 2. That value. What? Okay, now multiply both sides by 2. So now we know the distance between them is 0.684. Q over 2 times Q over 2 is Q squared over 4 times 1 over d squared, which is 0.684 squared. Okay.
Wait, hold on a second. Whenever we did the 0.342, wouldn't we take that and divide that by 2 since that's our new d, you know?
Now d over 2 is equal to 0.342.
Oh, okay.
We multiply both sides by 2 to get d, which is the distance.
Oh, you're just saying, you're just saying that's half of the diameter. Okay.
Or half the distance, yes.
All right.
So we multiply both sides by 2 to get the full distance between them. And that's the number that gets put there and squared as part of Coulomb's law. That distance squared.
Okay, so how'd you get the 4? So you took 2.
Q over 2 times Q over 2 is Q squared over 4. So we've got that number in terms of Q. Okay? But we don't really have anything we don't really have any way we can solve that. Okay? Not yet. But we do know that there is a third vector because these balls they're not moving. They're stationary. And that means that the sum of the forces must be 0 because their speed is not changing. So if their acceleration is 0, then the sum of the forces must be 0. That means we need to know this tension in the wire. And that force of tension must be equal to the vector sum of these two forces. Okay? Does everyone understand that?
Okay, so we just found the electrical force just a while ago.
We've started finding the electrical force. We've written down what we know we can run. We still don't have enough to say what Q is. Okay? But we do know that Q squared times K divided by 4 divided by 0.684 squared is equal to that electric force. If we had a number for that electric force, then we could solve this equation for Q. That's what we're looking for now, is the number that we can put here as the force, as the electric force, or as the horizontal component. Okay? Well, do we know that the magnitude of this vector, the total force? But we do know that this total force times the cosine of 26 degrees is equal to mass times gravity, the force due to gravity. Everybody see that? We don't know what this magnitude vector is. We don't really know what this magnitude vector is. But we do know this one. We know force due to gravity. That's 9.8 times 0.021. That's a number. We know this angle is 26 degrees. And so we know that this vector times the cosine of 26 degrees is equal to this vector. Remember, that's how we converted a polar coordinate vector into Cartesian coordinates. Okay? The very first, problem 15, we were looking at vectors. You've got x and y. This is your vector. There's your angle theta. The horizontal component is the magnitude times the cosine of theta. The vertical component is the magnitude times the sine of theta. That's how you decompose the polar coordinate magnitude into the horizontal and vertical components. Here, it's all turned, it's rotated and turned over, but you're still looking at the same trigonometric identity. The hypotenuse, here's your right triangle. The hypotenuse times the cosine of this angle is equal to the adjacent side of that angle. So, since we know that force total times the cosine of 26 degrees is equal to 9.8 times 0.021 kilograms, 9.8 meters per second squared times 0.021 kilograms, then we can find the magnitude of force total as being 9.8 times 0.021 divided by the cosine of 26 degrees. You see, we just divide both sides by cosine of 26, and that leaves us with an actual number that we know is the magnitude of this force, this total force vector. Okay? But now that we know this magnitude, we know force total here, we know the angle is 26 degrees. That means now we can solve for the magnitude of this opposite side, which is the magnitude of the force electric, the electric force vector.
So now we take 90 minus 26 and
Nope. Well, right here, we've got force total times the sine of 26 degrees will be equal to this vector. The hypotenuse times the sine of the angle is equal to the opposite side from the angle. These are the parts of a right triangle. The hypotenuse, the angle, the opposite side, and the adjacent side. Okay. The hypotenuse times the sine of that angle gives you the opposite. The hypotenuse times the cosine gives you the adjacent.
we need the sine since we're looking for the opposite right now.
Well, we've got this magnitude. We want to know this vector. This is the one we need a number for. Because once we know that magnitude,
We can plug that in.
we can plug it in here and solve the cube. Well, we know this magnitude times the sine of 26 is equal to the magnitude of the electric force. It's equal to the opposite side. Does everybody understand how that works? What I just did? Okay. Don't lose me yet. Keep up. This is about to get real cute. Remember I told you don't do any rounding off until you have to. Force electric is equal to the force total times the sine of 26 degrees. What's force total? Force total is equal to 9.8 meters per second squared times 0.021 kilograms divided by cosine of 26 degrees. That's force total. We multiply that times the sine of 26 degrees, and we get the electric force. The force electric, the horizontal component, this one here, that we can plug in there. Here's another one for your index cards and for your notes. Trigonometric identity. The sine of an angle divided by the cosine of that angle is what? That would be the tangent of there. So what we finally come down to is the electric force, the horizontal component here, is equal to 9.8 meters per second squared times 0.021 kilograms times the tangent of 26 degrees. That's just tangent 26 degrees is just sine 26 divided by cosine 26. Okay? That's a trigonometric identity. You're going to want that on your index card in your notes for exam time. Now, we got that. We now have everything we need to solve for Q. What is what's FE? 9.8 meters per second squared. Times 0.021 kilograms times the tangent 26 degrees, and that's equal to K Q squared over 4 times 0.684 squared. And from here, we can solve for Q. Multiply both sides times 4 and times 0.684 squared. We get 4 times 0.684 squared times 9.8 meters per second squared times 0.021 kilograms. Divide all of that by K, which is, we'll just write it now as a number, 9 times 10 to the 9. I'm sorry, oh, you're right, I left out tangent 26. Sorry about that. That'll definitely mess up the answer. That's all equal to Q squared. So to find Q, just take the square root of both sides, and there's your solution for Q, the total charge on the electroscope. We're going to be doing a lot of vectors tomorrow. So again, we impress upon you, tomorrow's lab is not one you're going to be able to make up. Don't miss it. Since we are now halfway, we're 2/3 of the way through this week and we still haven't started on this week's material, again, I want to impress upon y'all the need for y'all to not only get this homework from last week turned in, y'all need to get next week's homework, this week's homework done this weekend too. Because if I've still got most of the class a week behind come Monday, then I'm going to have to put the brakes on, on giving any kind of leeway for turning in late homework. I'm going to have to start docking points, and I don't want to do that. So, make a point of getting this homework done this weekend. Now, I will try my level best to get you through the rest of chapter 16 on Friday. I will, at the very least, try to make sure I get the hard parts that are going to be likely to cause confusion, to try and get them explained to you and get them recorded so you can go back and visit them. need to. But today, before anyone packs up like they're about to leave, we have got to get at least this part of chapter 16 under your belt before tomorrow. Coulomb's law tells us the force exerted between two charges. Q1, Q2 divided by the distance squared. We then talk about the force exerted on Q2 by Q1. Right? Well, Q1 does not actually touch Q2, does it? This is a field force. So, we come up with a term called the electric field. It is a vector field. We define it so that the force exerted on Q2 is a scalar, it's just a charge. It's not a vector quantity. It's a total charge. It has no direction associated with it. That means we have to define this electric field as a vector field, so that the force experienced by Q2 is that vector field times the charge Q2. Well, we know from this expression here that this force is equal to K Q1 Q2 divided by R squared. If we divide both sides of this equation by Q2, we're left with the expression of the electric field produced by charge 1 as K Q1 over R squared. Now, R is now no longer the distance between Q1 and some other charge. R is the distance away from Q1 that you are. So now you talk about a charge, a point charge, located somewhere in space, using this equation. You can talk about it as a magnitude, or you can talk about R as being the vector.
Okay, so R is no longer the distance.
Right. It's the distance, but not to the charge. It's the distance to any point in space around Q1.
Okay.
So if here is Q1, if you want to know the E field at that point in space, it's a vector. It's going to be pointed directly away from Q1 in that direction, and its magnitude will be K times Q1 over R squared, where that is R. You go to that position R away from Q. That's the magnitude of the electric field at that point. And its direction is pointing radially outward from Q. And if we did this in three-dimensional space, we would convert everything into spherical coordinates. So everything would be, instead of a function of x, y, and z in rectangular three-dimensional coordinates, it would be a function of r, theta, and phi. Theta and phi is the angle of rotation in the xy plane, and phi is the angle of rotation in the xz plane. Don't panic. We're not going there. Okay. We're not going into 3 dimensions with this stuff. But tomorrow in lab, we are going to start plotting out the vector field around 2-point charges. And that's going to be the whole lab. In fact, you're probably going to have to take it home and finish it at home over the course of the next week. Now, it's important to do because the week after this, next week, we're going to do a lab on equipotentials, on the potentials that derive from this electric field. And that's something that you're actually going to sit down here in lab and you're going to measure it and plot it out. And when you do, I want you to plot it on that same graph of the vector field that you build up from this week. Does anybody else have homework from last week? I really do want to impress upon y'all, please. Everybody sign the sign-in sheet. Do any of you want back your labs from last week? Wade Young, Dustin Taylor, Spencer Lawson, Jonathan Mercer. Cyrus is not here. Cody Winland, Devin Graham, and Dalton Smith. You bet. I will see you all tomorrow, and everyone else too. I hope.
You say you are uploading these lectures to the online classroom?
The ones that, I don't have technical difficulty with.
Okay.
This one looks like it recorded well.